Good. Hello, everyone. We're back with another episode of Computer Vision Talks. And today we are going to discuss yet another paper in the domain of continual learning. And we have with us Arthur Douillard. And we're going to discuss his work on PLOP, learning continuously without forgetting for continual semantic segmentation. And yeah, so talking about what Arthur does, it's going to be a very long list because he's a research scientist. He's also a PhD student at Sorbonne. He's also a lecturer. And yeah, he's been doing a lot of cool research, and I'm sure we'll be learning a lot more beyond continual learning today, because I have read a tweet from him and I would love to know and discuss with you about his journey of PhD and other research work. Regarding the paper, we are going to discuss more on continual learning, as we already know that continual learning aims to learn incrementally new classes without forgetting previous classes, and combined with semantic segmentation, which aims to classify an image per pixel. So over to you, Arthur. Would you like to introduce?
Yes, so thank you for inviting me to this presentation. So if I want to present myself a bit and also my team. So I'm currently working at Heuritech. It's a Parisian, so from Paris, startup that work in fashion. I don't really care about fashion, but it's more the objective that is really interesting, where we go over Instagram, Baidu, all over all sorts of kind of website, and we scrap the clothing, the images of people, and we are using algorithm, so convolutional neural networks, in order to understand what kind of clothing people are wearing. And it's very challenging because you have domain adaptation, few shot, a lot of noise, out of distribution. So there's a lot of challenges which are very interesting in this company. And one challenge that is very important for our company is that regularly, every week, there is some kind of fashion company that come to us and ask us, can you detect this kind of shoes, this kind of dress on the internet, please? And we can, but we need to retrain our model from scratch. And it's very complicated. And this is why I started my PhD thesis. So it's in partnership with Sorbonne University in Paris and Heuritech, where I'm working on continual learning, where the goal is hopefully that I will be able to make my company learn any kind of clothing, so shoes, for example, incrementally, but very quickly, without needing to review all the previous kind of shoes, dress, and whatever. So I think that's my presentation. And I'm working a lot with different kind of people, mainly in Paris, including Yifu Shen from Sorbonne University, Arnaud Depogny from Dakota Lab, another startup from Paris, and Mathieu Cord with my PhD advisor from Sorbonne University also. And he's also a scientist at Valeo, which is kind of a company about car and autonomous driving. So do you want me to start my presentation? Or?
Yes. I would love to move forward with the presentation.
Okay, so first I will begin by asking what is continual learning. So during this presentation, I will assume that most of you know most of the kind of deep learning, so all the forward and back propagation, etc. So what is continual learning? So usually when you're working in deep learning, pretty much I think all of you have probably trained a model to classify a cat and dog. And it's quite easy. And you are going to train your model once on a big data set, and then you are going to evaluate your model on a fixed test set. So it's quite easy to do it, and it's almost a solved problem in computer vision. But it's because we are assuming that the data is independently and identically distributed, meaning that there is one distribution that is fixed, and we are learning from it. But this is not really a good assumption, because, for example, if I'm adding new kind of cat, new kind of dog, so it could be new example, or it could be new classes. If I want to distinguish different kind of classes of cat and dogs, I'm going here to need to retrain from scratch our model. So it can be very slow and inefficient, but it is the way that most of us are doing it right now. And can we do it something better? So it's the goal of continual learning, because we cannot retrain every time. So it's very, very slow. So as you can imagine, for example, a company like Google or Facebook, they have a petabyte of data and they cannot retrain from scratch every time. So it's challenging. There is also some kind of privacy problem. So you can also find this all in the medical literature. So the thing is, Usually, if I'm taking the data, for example, for my body medical data, the hospital maybe cannot keep it for too long because of privacy issue. So you need to be able to train the model on it and then to simply discard data and hope that we are going to keep the knowledge of the data embedded in the network in some kind of privacy preserving way. And there's also, I think, maybe the most interesting method, the memory limitation. So if I want to have a robot in the wild, that's simply a walk among us. A robot is quite small usually and doesn't have a lot of disk storage. And if we want the robot to learn as a human gradually through his life, we need to be able to continuously discard the data and keep learning on the new data without forgetting the previous data. So this is all the motivation behind continual learning. And what you need to really understand is that the real world data is very, very rarely independent and identically distributed. So the problem is in continual learning, in deep learning and machine learning, we all work on mostly on toy data set, like even ImageNet, which is kind of artificial. But in real life, the data is always changing. So you have several situations. I'm only showing you here once. For example, there's new classes. So first I'm learning cat and dog. And then I'm learning boat and plane, and etc. But I want to keep learning gradually forever, new classes, without forgetting previous classes and without reviewing previous classes. So first, I'm going to show some kind of a very agnostic protocol that mostly work with every kind of models. So first, we're going to initialize our first model, so F0, and we're going to train this model on the first task, the 0 task. So it's at this point is very supervised setting. So it's simply, for example, if I was learning the cat and dog together. Then for all next task, I'm going to initialize my model from the previous model. So we have learned something in the previous task, so it will be stupid to not keep it. So we're going to keep the knowledge by initialize a new model with the previous model. So it's kind of like in transfer learning. But then we're going to extend our classifier because we want to predict potentially new classes, for example, cat, dog, and then plane and boat. Therefore, we need new classifier weights. So extend this classifier. But there is also other method that can also extend parameters at other points than simply the classifier. And then we're going to train our model on the new dataset. And this is the very, very interesting point, because at this point, it's very similar to what you can find in transfer learning, where you're learning, for example, on ImageNet, and then transfer your knowledge on a smaller dataset. But this is very interesting and important, is that we are not going to evaluate our model simply on the target dataset, the new dataset, but we're going to evaluate our model on all seen dataset. So from the first task to, so it should be 0, not 1, to the last task. So we really want to keep learning new classes, new tasks, without forgetting the previous classes. So I'm just going to make a small parenthesis about some kind of setting that is very important in continual learning, and it needs to be understood if you want to understand how continual learning works. So there's two settings in continual learning using single head or multi-head. So in a single head and multi-head, so we're going to have two tasks. First, the first task, we're going to learn cat and dog, and the second task, we're going to learn boat and plane. So in the final evaluation, for example, I'm going to show my model a new kind of dog. In single head, which is also called class incremental learning, I will need to classify my dog as a dog, a cat, a boat, or a plane. So among all classes. While in multi-head, which is called the task incremental learning, we're going to need to classify our dog between dog and cat, meaning that we know which kind of task does the sample come from, which can be a good assumption, but is more related to multitask learning, while the first setting, single head, I think is true continual learning, because in the real life, for example, a robot or even you as a human, you don't know from which task the sample is coming from. You simply need to classify it among all your knowledge. So dog, cat, boat, and plane. So I'm going to show you some examples. So why content learning is really hard and is very far from being solved. So here I'm going to show you an experiment on CVPR100. So at this point, there is a 10 point for the first point. So you can see my my mouse. Okay.
Yeah, we can see.
Okay, thank you. So at the first point, we're first going to learn a model on the first 10 class of CVPR100. And we're going to evaluate on the first 10 classes. Then at the second point, we're going to retrain from scratch our model. So we initialize and we train on the 0 to 20 classes, so 10 more classes, and we evaluate on all scene classes. So as you can see, obviously the performance is lower once we are going to learn more classes because the objective is harder, but it's not that much lower because we are going to retrain from scratch on all scene classes. But it's also very painful because it means that every time I'm adding 10 classes, I need to review all previous classes. So as you can guess, the computational cost is simply growing quadratically through time, which is not practicable. So what we want to do is fine tune. So simply I keep the original model and I'm not seeing previous data, but I'm simply learning on the new data. And we can expect that the previous data was kind of learned and embedded in the network and we won't forget it. But as you can guess, this is not what we can find. Here in blue, you can find the model that was fine-tuned on your new data. So they simply see the new data and then is evaluated on all scene data. So you can see here that the final accuracy of our fine-tuning model is 9%, which is super low, while the upper bound, so the model which was retrained from scratch in orange, is around, I think, 17. So it's much lower. But it's not interesting to simply look at the last accuracy because in a true continual learning, you'd never know at which point you're going to stop. So you can stop your model at any point. So it's very related to the anytime algorithm. So what we're going to want to find is the average of all tasks. So we're going to take this average, and average all points together. And you can see that the average here is 26%, which is very low compared to the upper bound. And this huge gap between the model that was retrained from scratch using all data and the model that was fine-tuned simply on the new data is enormous. And the gap is so strong and so big that the literature is calling it a catastrophic forgetting because it's very hard to solve and it's a problem for many companies. So I've finished to explain what was continual learning, and I'm going to explain what are some kind of the existing model in the literature. So if you have any question, you can just stop me right now.
It would be really great if you could just elaborate on one point here, that as the number of scene classes of the previous trained data is increasing, the catastrophic forgetting is increasing, or as the number of classes in the new data is increasing, then the catastrophic forgetting is increasing.
Excuse me, can you repeat, please? I'm not sure to understand the last part of the sentence.
So on the graph where we have accuracy on the y-axis and number of scene classes on the x-axis, and the orange one is retraining from scratch on all the scene classes, and the blue one is fine-tuning, right?
Yes.
So as the number of classes are increasing, the fine-tuning on new data is deteriorated, right?
Yeah.
Like if we have a large number of new classes, then fine-tuning will be even less effective.
Yes, so indeed, here there's a 10 step, but I did some experiment, for example, with 50 step, and the catastrophic forgetting is even higher. And at some point, your model at the end is almost random, so it's useless.
Okay, cool.
Yeah, and what is important, maybe I didn't emphasize on it enough, but here I'm showing you the accuracy on all scene classes. But what is also interesting,
I keep getting this doubt that when we are doing transfer learning, we are doing similar kind of thing, right? Like you have a trained model on some particular data set, and then you're trying to use that trained model on another data set, and the results are not so bad. But why
Yeah,
are
but
results?
in transfer learning, you don't care about the previous dataset. So if you're using a model from ImageNet which has 1,000 classes, and then you fine-tune a transfer on cat versus dog, which has 2 classes, at the end, your model only predicts 2 classes
Okay.
and not the previous 1,000 classes. Else, if you were in content learning, you would predict 1,000 classes plus 2 classes. So it would be much, much harder.
Mm-hmm.
And one thing that is very important to understand also is each point here is the accuracy on all scene classes. But it doesn't mean that if my model, for example, here has almost 45 accuracies, it doesn't mean that my model is okay-ish, is not that bad, because you need to distinguish that in this accuracy, there is the accuracy on new classes and your accuracy on all classes. And it's very important to see that usually if I'm looking at the end of the model, so once the model has learned 100 classes, and if I want to understand where is the model good, is it good on the first classes, the middle classes, or the end classes? And the result is not very intuitive, meaning that usually at the end, the performance of the model is very best on the last classes, which is kind of obvious because there's a lot of data, but it's also very good or quite good in the first classes, for example, the 10 first classes. And where the model is very, very bad is in the middle classes, because at this point, the model simply keep forgetting the middle classes. So it's not a very result that is very interpretable, and we don't really know why. Yeah, if you want to remember something, is that the performance of the model is very good on the last classes, on the first classes, but not in the middle classes.
Right. Got it. Understood now. Thank you.
Hi, Arthur. Would there be same trend like we see in the blue line if instead of increasing the number of classes, we simply increase the we let's say bring different type of species, like for example in the first task we are doing cat versus dogs classification, and in the second task we are again doing dog versus cat classification, but we are doing it more fine grained classification, like I bring different type of cat species here. So would this trend still be there, or it would be closer to the orange line here?
So it's a good question. So I'm answering you not when you're talking about fine grain. Like for example, if I'm doing a cat and dog, I still have 2 classes, but it's simply different kind of cat and dog, but still the same classes. So it's not
Yes.
class incremental learning, but it will be domain incremental learning. Another setting is, for example, I'm learning to drive in Paris, then in Bombay, then in New York, and it's always the same classes. So pedestrian, motorbike, car, road, but the environment, the domain is different. So it's domain incremental learning. It's a setting that is known, and the forgetting exists, but it's obviously much less. But there is still a forgetting, but it's yes, it's much easier than class incremental learning.
Okay, yeah, I expected that because maybe the structure would be same here. Instead of here, like we are bringing irrelevant classes like aeroplane and boat. So instead of that, if we bring different type of species, then the structure, the orientation would still be the same.
Yeah, yeah. So it's easier, but as you remarking, it's also depending on how much close or different are the domain. If I'm showing a specific cat or dog that is very, very different, we're probably going to be bad. But if the dog is simply slightly different, it's going to be okay. So it's in domain incremental, it's very important to understand how close are the domain.
Right. Thank you so much.
Welcome.
Great. I guess we can proceed.
Okay. So I'm going to explain quickly what is the literature doing in the broad axis strategy to fight off catastrophic forgetting. So I think there is 4 big methods: rehearsal learning, constraint, architecture, and classifier correction. So first, rehearsal learning, which is I think one of the most efficient methods, is simply we allow our model to review the previous data. We cannot allow the model to review all previous data because it simply will defeat the goal of continual learning, but we can allow to replay limited amount of previous data. So for example, if I'm working on Cypher, so each class has 500 classes. But when I'm doing a replay of reuse classes, I'm only allowing my model to see 20 classes per class. So it's much, much less. And rehearsal learning is very efficient, especially for large-scale dataset like ImageNet, where if you don't use rehearsal learning, it's really hard to have good performance. But some people say that, yeah, but I don't want to keep the data because there is some privacy issue. So what I can do is I can do pseudo rehearsal learning, where instead of storing an image, I can generate an image. So if I'm talking about generating an image, it means that I need to have a generator. So this generator can be quite anything you want, usually a GAN, and you're going to train a GAN. For example, here on the first task, I'm training my model on the first task and a generator on this task. And then during the second task, I'm going to ask my generator to generate new data from the previous classes. But there is several problems because for large scale dataset like ImageNet, it's really hard to generate informative images. So it's easy to generate missed digits, but if you want to generate a human, for example, it's much, much harder. And there's also another problem is, yes, so the generator can generate data and it will avoid our model to forget. But our generator can also forget. And this is a problem. And so it's again another problem, and you need to do some kind of protection for the generator, which is a bit complicated. And another point that you need to understand also, if I'm saying that when I'm doing rehearsal data, I'm allowing only my model to see, for example, 1 GB of previous data. But likewise, when I'm doing pseudo rehearsal learning, I should consider how much parameter, how much weight there is in my generator. Because if I'm doing using a GAN that is very, very large with extreme capacity, my generator can simply memorize by heart all the dataset, which again will defeat the goal of continual learning. Another strategy that is very, very important is the constraint. So what is a constraint? So I'm going to train a model incrementally, likewise, and I'm going to place a constraint between a model and its previous iteration. So what is the constraint is I'm saying that I want my model to have a similar behavior as the previous model. And how can we define this similar behavior? There is a lot of method. So there is method, for example, on the weight. So I simply can say that I want that the weight of my model, new model are close to the old model. So usually it doesn't work very well. So you need to weight this constraint by some kind of importance metric, meaning that important weights from the previous model need to be kept frozen, while weights that were not important in the past can be kept learning in order to learn new classes. There's also a constraint of the probabilities, where you're going to say, given the same image, I want my new model and old model to set the same probabilities. So it's the knowledge distillation of Geoffrey Hinton. There is also a constraint on the gradients, where I'm saying that I want my new model and my old model, given the same image, to have a gradient that are going in the same direction. And there is a constraint on the feature. So it's, for example, with PodNet, a paper I published last year at ECCB, where I'm saying if given the same image, I want the features, so the intermediary features at multiple levels of my convolutional neural network to have the same representation. So there's a lot of different methods to constraint, and usually in most of the literature, people are using one of them. There's also a modification of the architecture. So for example, you can have, as I'm showing here on the graph, you can have one subnetwork for the per task for in the whole network. So it's very related to the lottery ticket hypothesis. So I'm not sure how much familiar you are with this branch of the literature, but in the lottery ticket hypothesis, what the authors says is that in a very big network, there's also always a subnetwork that can be very good and very efficient. So it means that our model are over-parameterized and we don't need all the capacity. If we don't need all the capacity, some people say that simply we can use a small subnetwork, so some parameters in my network that can be used only for one task, and other kind of parameters that can be only used for another task. So as you can see here, we have the red and blue parameters that are only used for the blue and red task. Some parameters can be shared or not. So usually when you're doing this kind of thing, you need to have the task ID in appearance, meaning that we are in task incremental learning, where we know in which task we are in order to select the right subnetwork. But there is a very recent research that shows that we can do something without task ID. And how can we find those subnetwork? So it's not very easy. So there's several methods. We can use evolutionary algorithm like PathNet that was published by DeMine in 2016. Or we can use sparsity. So it's simply by a paper from Facebook. You can neural pruning. You can use L1 regularization on the activation in order to force your model to have a very high sparsity, and then you can simply truncate all the activation that are lower than a particular threshold. And one thing that is working very well is the learn mask, where you're going to have a mask, for example, one mask per channel that is learn, and that is learn to enable or disable a channel in order to create subnetwork. And I'm showing here how you can find subnetwork in the one fixed architecture, but there's also other kind of method like MNTDBPD, where you can simply keep the architecture and add new neurons around it. As it makes sense if you are assuming that you're going to keep learning, we cannot have a fixed capacity, therefore we need to extend the capacity. And finally, the last strategy is the classifier correction. So there is two methods that I know of that are very important. One is based on the cosine classification. So the author found that the magnitude of the bias and the weights were very biased against the new classes. So you can see here, like for example, here the weights and here the bias, that they are much, much higher for new classes than old classes, meaning that we simply overpredict the new classes against the old classes. And in order to fight this off, we can simply use a cosine classifier. So we replace the dot product of the classifier by dot product with the L2 normalization of the weights and the feature. And by doing so, the weights of our classifier, the magnitude of the weights are always 1. Therefore, we don't have an imbalance in the magnitude bias toward new classes. And another method is to do recalibration. So the miscalibration is when a model has, for example, a very high confidence, but actually it has a very low accuracy, because the confidence is not always correlated with the accuracy. And there is some method to recalibrate. So it's very easy with a linear model or isotonic regression. And you can simply, if you recalibrate, you can force the model to avoid over predicting the new classes. So it's kind of similar to the cosine method. And yes, so it was a cosine normalization that I was talking about. Okay, so I finished the literature and I'm going to start talking about my model. So if you have any question, just tell me.
And from my end, let's see if there's any in the chat box. So, yeah, one question can you move back to the slide where we were talking about confidence score? Yeah, calibration model. No, the last one.
Yeah.
No, next one. Yeah, this one. So how do we fix this? Like, how do we do this calibration? I know that if the model is giving very high confidence and yet low accuracy, then it is making wrong predictions very confidently. So that is a really bad thing. So how do we calibrate it?
Okay, so it's a good question. So maybe so to be very sure that everyone understands. So as you can see on the graph, the x-axis is the confidence and the y-axis is the accuracy. And you can see here on the right in the miscalibrated model that when the confidence is, for example, around at this point, is very usually the distribution of the probabilities is very biased toward very high confidence, but actually it's not very correlated with the accuracy, which should be a diagonal. And where you have a calibrated model, like here, it has a very correlation between the confidence and the accuracy, meaning that if my model saying, I think this is a dress with 0.6 confidence, it means that in 60% of the time, it is right. So this is a correlation. And how can we do it? So there's several methods, but I think one that is the most efficient, used by BIC, is to simply learn a small linear model. So they take the probabilities that are extracted on the validation set. So it's very important to do it on the validation set. And they're going to learn a linear model. So it's simply a scalar multiplied to the probabilities plus a bias. So it's simply two scalar. So it's very lightweight. And you simply optimize them to have a good matching compared to a validation data set. Considering that the whole model is frozen at this point, and you only train the linear model.
Understood. No, thank you.
Welcome. Okay. So if everyone is good, I'm going to start learning without forgetting for continual semantic segmentation. Please tell me if I'm going too fast or anything.
No worries.
So this was the work done with Yifu, Arnaud, Mathieu, and myself that we published at this year CVPR. So our method is based on constraint. So now you know what is constraint in content learning, and pseudo labeling. So I will go over it. But first of all, what is segmentation? Because it's very important because the field is different in continual semantic segmentation than continual classification. So in segmentic segmentation, instead of classifying one label for the whole image, you're going to classify one label per pixel, meaning that, for example, here on the kid that is blowing candles, so the kid is in red, which is the class person. The cake and the whole table is in orange, which is the class table. And behind it, everything is black, which is the class background. So the class background is kind of everything else that doesn't really matter, but you still need to predict. Likewise, for the cow, you have in green, and for the bird, you have in yellow. So we really need to classify each pixel. But why is it a problem in continual semantic segmentation? Because the very big difficulty is you can have multiple classes on the same image, and which change everything. So I'm going to take an example. For example, given the same image. So on the upper bound, on the upper row, you can see the ground truth. So this is what I need to predict. On the bottom row, this is what I'm predicting. So first I'm learning person, and I'm able to correctly predict all the pixels of person. But then on the second task, so here I'm showing you the same image, but it could be different images. I'm going to learn the class car. But at this point, we assume that we don't have access to the previous classes. And so we only see the ground truth of car, but we need to predict car and person. And likewise, in the third step, we need to predict here only the class bike, but then in test, we need to predict both car, person, and bike. So as you can see on the second step, at any point in time, you can have in the same image all classes and future classes. So why it is interesting and why it can be a good application. For example, if you're working in autonomous driving, so in autonomous driving, you know, all the video done by Tesla and other companies, usually they do a semantic segmentation where they want to classify each pixel of the road. So they want to say, here there is a road, here there's a pedestrian, here there's a motorbike, for example. But for example, if I want to learn at some point the bicycle class. So I'm going to get the images of bicycle, and I'm going to label all the bicycle in my images. But do I really need also to label all the images of roads? Do I really need to label by hand, which is very, very costly, both in time and in human time, in human cost, to classify all the pixels of roads, which I think my model should have learned. So it has a good application here in continual semantic segmentation, where we could simply label the new class and learn on this new class without needing to label the whole images. So there is two big problems and weaknesses of the literature in this situation. So the forgetting is really, really strong, even stronger than in classification. And we found that the previous state of the art did some kind of constraint, but that were too weak, meaning that they only constrained the final probabilities, which was not strong enough. The second problem is that we found that the images, as I said, were partially labeled. And this is a very important problem that we call the background shift. But the previous state of the art only maximize some kind of the sum of probabilities between the background and the all classes, which kind of was a tweak in order to work around this background shift problem, but didn't tackle directly the problem that the images were partially labeled. So first, I'm going to talk about the forgetting problem. So what we wanted to do is we did in last year ECCB model for continual classification that was called PodNet, and that used a new constraint called pod. So pod is a constraint that is applied at multiple levels in the intermediary features of your convolutional neural networks. So in practice, you have a ResNet, you have a 4 block of ResNet, and at the end of each block, you have features. And we're going to do a constraint between the new model and the old model of those features. So how can we do this kind of constraint? So we thought about simply doing an L2 distance between the features, but it wasn't working at all. So in my ECCV, if you want, I can send you the link, or we can chat about it later. L2 distance between the features was not working at all because the constraint was too indiscriminative and too strong even on uncertain pixel. And what was working very well was to not doing L2 distance between the raw feature, but rather to do L2 distance between the statistics of the feature. So how can we get statistics? There is a lot of way, but the best way that we found was doing a height pooling and a width pooling. So simply, we're going to average a whole axis, so the height axis or the width axis. So we have two kinds of embedding, and we're going to do a L2 distance between those two embedding between the new model and the old model. So as you can see here, the yellow are the width axis, the width pooling, and the red are the height axis. So pod was working very, very well in image classification for continual learning. And we thought, why not using pod to tackle the forgetting in continual semantic segmentation? So here I'm showing you the result of pod. So the matrix is the mean IOU. So the IOU, also known as Jacquard index, is simply saying how much the predicted mask, so the predicted pixel that I have predicted on my map, how much are they overlapping with the ground truth. So is my mask, predict mask, okay or not? So the metric is between 0 and 100, and being higher is better. I'm showing you three kind of metrics. So all is the final performance, so the final mean IOU on the final all task. Average is the average between all tasks. So as I've shown before, after each task, I'm doing an average. And 0 to 15 is the performance on the classes of the first task. And 16 to 20 is the performance on the incremental classes, so the new classes. And you can see that knowledge distillation, which was simply a constraint between the probability, was not working very well. So we only had a 23 mean IU, which is very, very low for Pascal Bock. So then we saw that UNKD, which was the CVPR from last year, that was doing some kind of knowledge distillation, but as I said before, what was summing the probabilities of the new classes with the background classes. It was working better up to 27. And when we introduced pod, it was working much better up to 34, especially on the all classes. So the first column, where you can see that we are much higher than previous state of the art. So the result was very promising, but we thought that we maybe could better. And why pod was not as efficient as we hoped? Because pod was designed for classification, while our problem was segmentation, which is totally different. Because in pod, as you can see, now that you understand what is pod, we did width and height pooling, meaning that we are summing, averaging a whole axis, and meaning that the whole images, which can be very, very large for segmentation, is completely summing across an axis, which makes sense in classification because at the end of your convolutional neural network, you have a global average pooling and then a classifier. So we don't really care about features here or here on the feature maps. We care about the average features, which is okay in classification. But in segmentation, we never do global average pooling because we need to be able to classify every distinct pixel. So not only the global features matter, but also the local features matter in order to classify simply multiple objects and multiple places in the image. Therefore, we thought about extending our model pod into a local pod. So we did a lot of experiment doing something more complicated, but at the end, this was the simplest solution, simply adding multi-scale that worked better. So in the first box, you can see the pod embedding with the first scale. So it's simply a pod embedding on the whole feature maps. But then we can also do pod embedding on a smaller scale. So as you can see here, I'm doing a pod embedding on a quarter of the feature maps. So I'm doing one pod embedding here, one here, one here, and one here. So as you can guess, when I'm doing a scale 1/2, I have 4 pod embedding, 4 pod embedding versus 1 if I'm doing simply a scale 1, meaning that we're going to put more emphasis on smaller scale than larger scale, which is interesting in segmentation. And what were the results? The results were much better to our surprise. Especially in the performance of the all classes, so where the forgetting can be strong, you can see that pod, which was our state of the art, we surpassed it by 20 points when doing a multi-scale approach using local pod. Likewise, we improved the performance of the new classes and especially the old classes, so all scene classes, by again 20 points. So local pod was very interesting, and I think it's important when you're working in any kind of subject, for example, like here in a continual semantic segmentation, to incorporate some kind of intuition about what kind of data you're working on. If we are working on the data and we don't really care about what is it, but simply just features, but it can be very complicated to make it work. And we make it work because we thought what was our data. It was not classification, it was segmentation. And we use this prior. The second problem is the background shift, where images are partially labeled. So how we can tackle it? So in the first step, for example, I'm going to learn the class person, and I'm going to predict person. So my prediction is not always perfect, but it's good enough. Then in the second step, so I'm showing you here always the same image, but usually it can be just different images. So in the second step, I'm learning the class table. Only the class table in orange is labeled, while the previous classes, person is not labeled anymore. What we're going to do, because if we are going to learn on it, we're simply going to forget the class person because it's not labeled anymore. So we need, our model is told to simply classify it as background, which is not true. So we're going to use the previous model to do a pseudo labeling, meaning that our previous model is going to predict, like we will do in inference for testing, is going to predict on the pixels that are background. So obviously it's not going to predict on the control pixel of table because we know that they are table, but we're going to pseudo labelize on the pixel of background because we don't know if the background is really background of all classes, and we're going to complete the feature maps with person. And then our model can learn on both table and person. Likewise, if I'm doing a new classes, a bottle, I'm going to do labeling here from not the first model, but from the second model, which has learned table and person. And we're going to complete the control using person and table and giving this prediction. You can notice that we highlighted differently some pixels. So for example, for the table, there is some strong bold yellow and light yellow pixel. The light yellow pixel were uncertain pixel. So how do we define the uncertainty? So there is a lot of way, but we base this on a work of our colleague, which was working on the entropy. So if the entropy of our model, of the old model, so here the second model is very high on pixel, higher than some threshold, we are saying that the whole model is not certain about this pixel. And if the model is not certain about this pixel, we don't want to pseudo-labelize. Otherwise, we will simply propagate errors, and it is very, very bad. Therefore, this kind of pixel, we simply discard them, meaning that we are setting it to some kind of special label called unknown in the literature, where we simply doesn't use those uncertain pixels in the classification loss. So here I'm comparing different methods about our technique of classification. So if I was doing simply crossentropy, CE, or crossentropy only on the new pixel and not the background pixel, the performance are very low. UNCE, so it's again from the same paper that did UNCD, which was the last year CVPR, they merge the prediction of all classes with background. So it's simply saying that it's okay if you're predicting either background of all classes, don't really fuss about it. And it was working much better than simply using CE with a quite simple method. But we found that by doing a pseudo labeling, it was working even better in all metrics for both old and new classes. And we were wondering, there is a problem because we're using the pseudo labeling of the old model, and the old model may have forgotten. And if he has forgotten, the pseudo labeling will be bad. So we compare with the pseudo oracle, where the pseudo oracle is how will our model fare if all the certain pixels were correctly labeled. And we found that the pseudo oracle it was not that much better than our pseudo model, which was quite reassuring. So I made a small ablation of what kind of pseudo labeling we can use. So the naive model is simply pseudo labeling every pixel of the background, and we don't discard any pixel. You can also use some kind of thresholding. So simply a thresholding by 0.9, for example, saying if a pixel has a confidence lower than this, I'm not considering it. Or median, if the median, if the confidence is above the median confidence or not, etc. And we use also the entropy. So the entropy, so it was our final model. It was not the pseudo labeling that was working the best, but it was the pseudo labeling that was working with the best equilibrium between all classes and new classes. And one thing that was also very important is that we use an adapted sample weight, meaning that if we discard a lot of pixels for some classes, for some images, because the background was mostly uncertain, it means that we're going to have much more new pixels that are labeled comparatively. And because of this, we're going to overfit on the new classes, which was a problem. Therefore, what we're going to do is, if our old model said that a lot of pixels are uncertain, we're simply going to lower the overall sample weight of this image, meaning that this image is globally uncertain and we don't want to take too much weight on it. This innovation was very important to make it work. So now I'm going to show you what were our results. So we did the experiment on several datasets, including Pascal block. The Pascal block is a dataset with 20 classes. So that experiment in 19.1 and 15.1, for example. So 19.1, we're going to learn 19 classes, then 1 classes. 15.1 is we're going to learn 15 classes and then 5 classes. So both of them are 2 tasks. So it's not very interesting, I think, to do only 2 tasks because the regime of continual learning is not the same with 2 tasks or 10 tasks. So it's very different. So we did more experiment in 15.1. So we are going to learn 15 classes, then 1 classes, then 1 classes, every time up to 20 classes. And you can see here that the previous model, so AWC, ELT, MIB, were very bad, almost random, while our performance was much higher with a performance in all class that was almost double than the previous state of the art. We also created a new setting with even more tasks, so 10.1, and we saw that our model was still much better than the previous state of the art. So now we are working in continual segmentation, so it's always nice to have some visualization. So here, for example, I'm going to learn 15 classes. So at first, MIB and PLOP, so MIB is the latest state of the art from last year's CVPR, have the same prediction because they're simply learning the first task, which is kind of a supervised learning. Then we're going to add new classes. And as soon as we add new classes, you can see that the MIB completely start to forget everything. And MIB predict, for example, for the bird, instead of predicting bird in yellow, it is predicting the class sheep. there is no table anymore according to MIB, and it's predicting a train instead of a table. So MIB completely forgot the old classes and hallucinate the new classes, while our model PLOP managed, with some imperfection, to have a very good stability. So here on the images, I'm only showing you on the situation where all classes present in the image were classes from the first task. What if the ground truth change, meaning that in the same image, there is classes from past task and future task. So as you can see here, in the first task, we're going to learn person. Then in the fifth step, we're going to learn train, meaning that the ground truth of my model, of my images, has changed. And therefore, we need to change our prediction. MIB changed, but too much, because it's only over predicting the class train, and at the end, there is no anymore person on the image. While PLOP managed to predict both person and train, thanks to our pseudo labeling, because we can pseudo labelize a lot of person in the images, and in order to retain this knowledge. Okay, I don't know if do I have still time?
Sure, time is not a worry here. You can finish.
Okay, so I'm just going to show you a quick extension of my work. I presented you my paper that we published at CVPR, and we did some work on this, and we're going to publish in a journal an extension of this model, where we consider if the pseudo-labeling was really that good. And there is a big failure case of the pseudo-labeling is how can you pseudo-label if there is nothing to pseudo-label? And this is a problem. For example, in the fifth step of the on Pascal book, the fifth step, there is a lot of pixel of train. So train here is this class. So there is 32% of the pixel that were train. Most of the pixel obviously is background, so not interesting. There is a little bit of person pixel, but then there is no cat, no cow, no dog, no bird, nothing, only train classes. Meaning that here, our pseudo-labeling loss can find a person and pseudo-label person, but nothing else. So this is a very big problem. So what we wonder is how can we deal when in those kind of situations? So our solution was to do rehearsal learning. So as I said before, we allow to reuse the previous amount of the previous data. But we cannot do simply rehearsal learning naively, because the sample, for example, from the first task has a partial segmentation map, because it may contain classes from the future that I'm going to learn maybe in 1 or 2 tasks later. Therefore, every time I'm seeing a memory sample, I need to also pseudo-labelize this memory sample. So it's very important. So if you were not doing a pseudo-labeling, this won't work very well. And there is also another problem is the segmentation images are very large. Usually, when you're working on Cipher, it's super small, like 32 by 32. ImageNet is quite small, so it's almost 200 by 200. But in segmentation, is usually 500 by 500, or even 1000 by 1000 pixels. So there is much more pixel, meaning that the images are also much heavier. And if they are heavier, we cannot store too much images. Yes.
So why don't we do like an object detection first, extraction then, and then the segmentation? If there's so much of
I'm going to talk about it. Don't spoil.
Oh, sorry.
But it's a very good remark. So the image are very heavy, and as you well remarked, also the image are mostly useless, because on Pascal Voc, 63% of the pixel are background, which is not very useful, or 32% of the cityscape are roads. So yeah, okay, we need to classify roads, but at some point our model know how to classify roads. We don't need to see every time roads. So can we store only what matter? And so it's mostly the same solution that you propose. So I don't need to do object detection, because I have the ground truth. So because I have the ground truth, I can simply do a segmentation and extract the images, the object that I want. So I'm going on the previous task to extract some objects, so which are super lightweight. So, for example, you can see a dog, a bird, and a bus. Then we're going to pass the object on the current images. So as you can see here, I'm learning sheep, and I'm going to pass a bird on the sheep. So you can ask how to pass the bird. Should I pass it on the middle, on the left? There is no really a good intuition about it, and the literature is not always very consistent. And usually you can pass it randomly or at the same place that you found the bird originally. So it's not very interesting. But what was very important, because this was not working, and how to make it work correctly. Because on this situation, when you're pasting, even if you find the right place, the ideal place to paste your bird on the sheep image, there may be interference because the pasting is not perfect. And sometimes the boundary pixels are ugly or this kind of stuff. So the best method that we found, it was selective erasing, something that we didn't find in the literature, where we simply choose to erase all foreground objects. So we do the labeling in order to see what kind of foreground object there are in the image. Then we erase it. So simply we replace by a gray pixel, and those pixels are discarded in the classification loss. And then we are pasting the object on this. And this method was essential to make it work. And I will show result why later. So in order to show some result, so I'm showing you PLOP. So PLOP, which was from this year CVPR, our state of the art. We then improve PLOP with some method using cosine normalization, using a batch renormalization instead of batch normalization, and a lot of small tricks, and we managed to have a much better performance. So we increase from 54 to 61 the performance of our state of the art. And then we considered a different kind of rehearsal learning. So it was from a paper from EPITA, which was using an external dataset, which could be VOC or COCO. So it's a big dataset, and we simply going to pseudo-labelize it and to do rehearsal. So the performance are very good, but the memory overhead is gigantic. So it cannot be used likewise. Then we do with PLOP-long our partial VOC. So partial VOC is rehearsal learning. So rehearsal learning with the whole image, but because we call it partial, because the images are partially labeled and we need to complete with the pseudo labeling. So the performance are very impressive. We have 66 mean IU in all compared to 54 of our model, but the overhead is quite is okay. It's only 22 megabytes, but it's still too much according to us. And here we are using the object VOC. So it's our solution where we simply going to pass the object, and we have as much or even better performance than using partial VOC, but which almost a 10 times lower memory footprint, which was very interesting. And the memory footprint here of the partial VOC, which use the whole image, is quite low, like 22 megabytes, but because the Pascal VOC are quite medium-sized images. If you're working on larger size images like cityscape, the footprint is enormous. It's almost 100 or 200 megabytes, while our method of object VOC, object cityscape, is less than a megabyte. So it's really important to do object rehearsal instead of image rehearsal if you're working with large images. And I'm showing you quick images, so it's an ablation, and I will be finished. How we did this kind of pasting and rehearsal. So there's three kind of rehearsal that we can do. So it's an image rehearsal where we rehearse the whole image, the patch rehearsal where we rehearse so the object and all surrounding pixel. So we copy all the surrounding pixel with the object in order to rehearse it. Or there is the object rehearsal where simply we're copying the pixel of the object and pasting elsewhere. So obviously, image and a patch have a much higher memory footprint than object, but the patch was okay. Then the notion is how can we do the mixing? So how can we paste? So we tried several methods. Simply we were pasting, or we did a cut mix up. And we even tried to do some mix-up or pasting in the pixel space or in the feature space, but at the end, the pixel space was working best. And the pasting method was working much better than mix-up. And then we also considered some method, what to erase. Do we need to erase some pixel in order to make it work correctly? And the answer was yes. So for example, if you see the before last line, so the line number 9, you can see that we did object pasting, but without erasing anything, and our performance was 63. While if we did some erasing of only the foreground objects before doing the pasting, we have a performance of 67, which was much higher, and which shown that the erasing was essential to make object rehearsal works. So with this, I finished in 1 hour sharp. So do you have any question?
Okay, so in the audience, if you have any questions, either you can unmute and ask yourself, or you can put it in the chat box and I'll ask it for you. Till then, I have a lot of questions, not necessarily related to this paper, some general ones also. So since how long have you been working on this paper?
On which one? The second one or the first one? The second one?
PLOP, the first one.
PLOP. How long? It was quite quick. So I was wondering. So I published last year my podlet at CCCV, and then I did some literature review of all CVPR that were published at last year, and wonder what was the new problem I could attack. So it's always hard to, as a researcher, a PhD student, to know what to attack. So you need a problem that is interesting because you need to have fun, but you also need a problem that can be attacked. Because some problems are too hard to make it work, and it's also nice if the problem is interesting for the community. So we chose to do a segmentation because it was very interesting, and there was a paper from last year that shown that we could do something, and we had some idea how to make it work. So very quickly, we knew that we wanted to do. Very quickly, we knew that we wanted to do both the pseudo labeling, which was, I think, obvious to us. And we also wanted to try our pod distillation loss, because the pod was working very well in our previous paper. Then we had some difficulty to make it work in practice, so with the local pod. We started the last year in August, and we finished, I think, in sometime in November, something like it.
Right.
So maybe like 4 or 5 months.
Yeah, that was good. So you were already working in this domain, right? Before starting the paper.
So no, I never worked in segmentation before, so I knew nothing about segmentation, but I knew quite well computer vision. But segmentation is quite easy because object detection, you need to understand what kind of object, and you need to have a region proposal network. It's really, really hard to make it work. But segmentation is simply classification, but per pixel. So it's simply cross-anthropy loss, and it's quite easy to make it work.
Right, right. And if I ask you, what was the role of your collaborators or your supervisor in this paper? What would you like to say?
I was the main author, so I did all the coding and most of the thinking. But Ifu was alongside me. So Ifu is much better in mathematics than me. So we wondered some intuition about the maths behind our model, and we tried a lot of different losses together. So we chat a lot. And Arnaud was as a role more likewise than my advisor Mathieu. So they were a little behind, and we chat like once a week, and they helped me to write the paper.
Right. Okay, that's great. Another question would be, okay, so I already understood that part, that the new part was segmentation for this paper. Coming back to where I got to your paper initially was the tweet. So was that paper a different paper that you tried getting into CVPR last year?
Yes. 1 minute. So yeah, PODs, it's the paper that we published at ECCV last year, and it was indeed the paper that I tried to publish at CVPR last year, but was rejected. but it was not rejected by a lot. So I think I had some chance.
Yeah, so the first paper is close to our heart usually.
Yeah, I guess so.
Yeah. So yeah, one last question from my end would be that you chose this domain like continual learning on your own, or was a supervisor working in it, so you ended up getting chosen?
I think like pretty much any PhD student, we don't really know what we want to do at first. So no, I wanted to do a few shot learning or domain adaptation, and then my supervisor sent me an email about some paper that was, hey, it's interesting. What do you think about it? And I really like it, and I really like all the methods in order to reduce the forgetting for human. So there is a lot of method based on the spaced repetition learning in order to reduce the forgetting for humans. So it was something that is my main hobby. So I thought that what if I could do my work the same thing but for machine? What if I could make my models not forget anymore?
That's interesting. And yeah, today itself I was reading a blog where they were saying that maybe it is it is a little a very small part of the huge term AGI, artificial general intelligence. Maybe continual learning could be a part of that as well.
Yeah, I think it's really important because you cannot expect to scale as a human if you don't are not able to learn simply continuously.
Right, right. So that was all from my end. Do we have any questions in the chat box? None. Great. So we would like to have your slides. If you could upload them on your
Yeah,
GitHub and share a link, I would add it in the description box, because else people keep mailing us or commenting on the YouTube video to ask for slides.
yeah, sure. I will send the slide. Sure.
So we look forward to a lot of great work from you. And
Thank you.
yeah, thank you so much for coming and explaining everything in so much detail.
Thank you for inviting me. It was nice.
Thank you. Have a great day.
Thanks.
Thank you, Arthur.
Thank you.